So last time we ended with looking at a number of different situations where we could look at a function f of x and determine where it was not going to be differentiable. What we now want to do is go back to our conversation about connecting graphs of functions with graphs of their derivative functions, and we want to think about, well, what will these, some of these various situations mean in terms of what we see on the graph? So that's what we kind of want to go back and take a look at. So we're going back up here to the last page. And so we had just kind of made some of the early beginning observations when we were working on this last time. And now we're going to get into some more details here. Oops. Okay, so first thing we want to do then is think about the vertical tangent lines. So we had two situations of vertical tangent lines at the end of our last discussion there. And so one of them is, I guess, what I would call the regular vertical tangent line, and the other one is what I would call the cusp point. So we have two different types here. So let's even kind of observe that. We have what I'm going to refer to as the regular vertical tangent line, and then we're going to have the cusp point vertical tangent line. Okay, now if we think back, so bear with me when I scroll up and down here. So let's go and look at these two situations here back on the last page of what we had summarized here. All right, so let's scroll down. Okay, last two. Vertical tangent line, the regular type, the second to the last one. In that situation, when you come from both sides, the slope of the tangent line from the left and the slope of the tangent line from the right both approach the same infinity. In a cusp point, slope of tangent line from left, slope of tangent line from right, those are going to different, opposite infinities. Okay, so keep that in mind. Regular vertical tangent line is going to the same infinity. Cusp point is going to opposite infinities. All right, but in either case, so let's think about the regular case in this situation. So we're saying that kind of even the notation that we had for the regular, so let's even think about that. I'm going to jot it down while we're working, and then I'm going to erase it down here. But in the regular, what were we saying? We were saying that the limit as x approaches that whatever particular point we're talking about from both the left and the right in the regular situation, so those, the limit as x approaches a of f prime, those were like either both going to infinity or they were both going to negative infinity. So think about what that means on a graph of a function. Yeah, it's f prime, but what does it mean to say as you get closer and closer to a from either side, you're going to infinity? So as I approach a from the left, I'm going to infinity. As I approach a from the right, I'm going to infinity. That means you have a vertical asymptote. Or they might both be going to, negative infinity, but still a vertical asymptote. Now, what happens on a cusp point? So on a cusp point, again, let's think about this graphically here. So in a cusp point, the limit as x approaches a from the left might be going, let's say, to positive infinity, and from the right, so again, we're talking about limit as x approaches a from the right on f prime, that's going to negative infinity. So they are going to opposite infinities. So let's think our way through that on a graph. So on a graph, if I'm getting closer and closer to a from the left, if from the left I'm going to positive infinity, and from the right I'm going to negative infinity, still a vertical asymptote, just going to different infinities. So both of these situations, both the regular and the cusp, both of these, if there is a vertical tangent line, both are going to mean that they're going to vertical asymptotes on the graph of f. So both of them are going to vertical asymptotes. So both are going to vertical asymptotes. Okay, going to, again, a vertical asymptote. Okay, so the only difference is in one situation they're both going to the same infinity, and in the other situation, they're going to different infinities. So for the regular vertical tangent line, if you will, the non-cusp type, this was the one where the graph is going to, and again, you got to think about that graph I just sketched, they're going to the same infinity. That's a weird way to say this. Let's say they're, so let's actually just do it this way. So you're either going to have, I'm even just going to do a little sketch right here. So you're either going to have a situation where maybe they're both going to the same infinity, like both going to positive infinity, or again, this is like, let's say at some point x equals a, again, here at some point x equals a, maybe they're both going to negative infinity, okay, but they're going to the same infinity. Now, when you had a cusp point, they were going to different infinities. So maybe at x equals, again, a here. So maybe from one side you're going to infinity, and from the other side you're going to negative infinity, or vice versa, right? So at x equals a, little asymptote here. So maybe from the right you're going to positive infinity, and from the left you're going to negative infinity. Okay, so that's the key observation, I guess I would say, to make here. So with the regular vertical tangent line, you're going either both to positive infinity, or they're both going to negative infinity around that vertical asymptote. If it was a cusp point on F, then one is going to positive infinity, one's going to negative infinity. Okay, so this is what's happening on the graph of F prime. All right, so now let's think about, well, what about the corner points? That's actually easier. So let's scroll back down, take a look at corner points. So that was really just even like this opening example. So with a corner point, the limit as x approaches c from the left of F prime is going to one number, and the limit as x approaches c from the right on F prime is going to a different number. So you're going into different values. So again, think about this, even just sort of writing out that notation. And then again, I'm going to erase that when we're done here. But let's suppose that we have, so suppose I was looking at the, so in this situation, suppose that the limit as x approaches a from the right of F prime sorry, weird. I've never had that happen during the video. I don't know if you saw that my phone call actually just popped up there. Weird. Okay. So the limit as x approaches a from the right of F prime, suppose that's going to 1. And then suppose the limit as x approaches a on F prime, so the slope of the tangent line from the left, let's say, is going to 2. So what does that mean on the graph of F prime? So as I'm getting closer and closer to a from the right, I'm coming into 1. Oops, that's not 1. I'm coming into 1 from the right, and the limit as x approaches a on F prime from the left, I'm coming into 2. We have a jump discontinuity. So from corner points on F prime, you're going to have a jump discontinuity. Okay, so that's what we're looking at here. Okay, so corner points are going to become jump discontinuities. All right, so let's see here. New color here. So let's say these are going to be jump discontinuities. All right, so it should be said that both of these situations on the last two, they are both places where F prime does not exist. So in one situation it might be a vertical asymptote, in another situation it's this jump discontinuity, and let's be extra specific here where the point doesn't exist. Like it has to be an open circle on both because f prime does not exist there. So these are both situations where f prime does not exist. So on these last two sets of things we were talking about, these are where f prime does not exist. All right, so with that, now let's take a look at a graph or two with some more interesting situations happening. All right, so here's what we have. We have a situation where, and now based on what we've talked about, in this situation, the blue function, we have this corner point right here. And sometimes I'll be honest, visually, it's a little hard to tell sometimes if it's a corner or a cusp on a graph like this, but we have the benefit of having the graph of f prime also on this graph. So visually, what is this saying? This is saying that the slope of the tangent line from the right, like the slope of this line right here, the slope of this tangent line, so the slope of the tangent line from the right is what I have drawn here. That's equal to -1, and that's why we're approaching -1 on the derivative. And what is this, the slope of the tangent line from the left? So this is saying that our slope of the tangent line from the left is equal to 1, and that's why we're approaching 1 on the graph of the derivative function. So that is what we're looking at here. So this one, very quickly, just based on the information that we've talked about, this is going to tell us that the blue function is the f, and the red function here is going to be f prime, just based on what's happening where f prime does not exist. And of course, the usual culprits are there that we talked about last time. Places of horizontal tangency are going to go to 0 or x-intercepts. So places on f where the slope of the tangent line is 0, those go to 0 on your derivative. Those are other things we talked about. And again, last time we talked about, or 2 times ago perhaps it was, so just to kind of recap these concepts here, where an original function is increasing means its derivative is above the x-axis. So where the original function is increasing, derivative is positive. Where an original function is decreasing, its derivative is negative. So where the original function is decreasing, its derivative is negative on that same interval. Okay, number 4, we're actually going to just sketch, thinking about some of the things we've learned. We're going to sketch both f, obviously, that's just the absolute value of x, and f prime. So our absolute value of x here is the original function. So let's just go ahead and quickly sketch in absolute value of x here. Okay. Well, I hope now, based on some rather lengthy, and I apologize for that, conversations, we can see that we have a corner point here at x equals 0. And if you know anything about your absolute value function, it's just the line y equals x in the first quadrant and the line y equals -x in the second quadrant. So the slope of the tangent line, really when it's a line, just the slope of that line, the rate of change. So the rate of change here, so the slope on this side is simply equal to 1. So on the derivative, it's going to be, for everywhere greater than 0, it's just going to be up here at 1. And then for the values of x less than 0, that slope is -1. So that just means the derivative is simply a constant at -1 for x is less than 0. However, remember, f prime does not exist at that corner point at 0. So these both must be open circles. So what we're observing here is what we summarized up above, places where there are corner points, numbers 2 and 4, excuse me, are both examples where there's this corner point, or sometimes we say this sharp turn in the graph. Those are going to be these jump discontinuities where the point will be an open circle because the point does not exist on f prime. All right, let's just look at, I'm going to squeeze in one more example here, just a number 5. Excuse me. So number 5, one last little example here. So suppose we have a function that has a graph of a cusp point. And so I'm going to draw in f, and oh, that was not good. Let's try that again. Okay, so I'm going to draw in f, and it has a cusp point here at the origin. And just for added clarity, I'm even going to draw in, not with a dash line, I'll just draw in even like this vertical tangent line here. I don't know if the arrow is helpful, so I'll just draw it in red just like that. So I'll leave it like this just to signify that that is the place of that vertical tangency on that cusp point. So what you see in red there. So here's my axes, and then just kind of what's in red is an attempt just to emphasize here this vertical tan line. Okay, cusp point. So at a cusp point, remember, and you can even kind of draw in, I don't want to draw in that same graph, so if you were to draw this graph again, what's happening, the slopes of the tangent lines from the right, okay, these are all positive slopes, but they're getting steeper and steeper and steeper. So this is saying the limit as x approaches 0 from the right on f prime is going to infinity. Then if you look at your slopes of your tangent lines from the left, again, these are also getting more and more steep, but this time the limit as x approaches 0 from the left, so our slopes of the tangent lines from the left are getting more and more steep, but they're negative slopes, so those are going to negative infinity. So on the graph of f prime, you're going to have a vertical asymptote. So let's draw that in here. So this is my vertical asymptote on f prime. And then we're going to different infinities. And in particular, from the right, f prime is supposed to be going to infinity. So from the right, I'm going to infinity. I'm going to clarify what happens on the ends in just a second. And then as I approach 0 from the left, my f prime should be going to negative infinity. So f prime is going to negative infinity as I approach 0 from the right. Now, what's happening on the ends here? Well, I mean, I guess basically if you just kind of look at your graph even, the little crappy one I have off to the right, what's happening to the slopes of these tangent lines as this graph is getting closer and closer to horizontal? Remember, if a function itself is horizontal, then its rate of change, its derivative would be 0. So these slopes are getting, looks like they're getting less and less steep, at least on my graph. They kind of look like they're flattening out. So I'm just going to kind of have these curves approaching, kind of getting smaller here and just sort of approaching 0. I didn't really specify when I drew it. I wasn't totally thinking about that portion of it, but I've kind of leveled off that the original function there, f of x, got pretty flat on both the ends. So we're just going to say that those are approaching horizontal tangent lines. They're getting flatter. And so as they get less and less steep, they will be approaching 0. So we'll just kind of have that on our graph here of f prime. But what I really want you to observe on this one is the notion of where f prime did not exist. So this is key. So right here, we're just going to have our little note here that this is where f prime did not exist. So just kind of be aware of that. And so there's two ways that when you're drawing your graphs, after you've observed that f prime does not exist, there's kind of two, so that's what we're just sort of noting here, just noting that f prime does not exist at the origin. And maybe let's even just extend that observation here over to this graph as well, right? So f prime does not exist at that sharp turn. So let's just kind of make that observation here as well. So both of these situations, f prime does not exist at x equals 0. But that can mean two different things graphically. Could mean something like this jump discontinuity with open circles. Could be a vertical asymptote like what we had on number 5. So again, just kind of looking at some of these different scenarios that emerge when f is not differentiable. Okay, so next time we'll just come back and maybe wrap up with one more, just more of a computational example.